Hello, my name is Megan Burfoot and I will be speaking on behalf of myself, Dr. Ali, Nicola and Amir. We are from the Auckland University of Technology and the title for this presentation is Developing Virtual Classroom Environments for Intelligent Acoustic Simulations. Within architecture, computer modeling simulations can provide valuable insight into building performance, especially in early design stages. Nevertheless, it is often challenging to ensure the quality of simulation results, suggesting that simulations should not generate solutions or answers, but increase understanding of the implemented model. For such simulations, we need an exhaustive amount of simulation data. Physical architectural environments comprise of many unique independent variables and unpredictable interactions between these multiple factors. Simulation of the physics of interactions is vital in understanding and accounting for their effects on building performance. Classrooms are commonly thought of as single-use spaces, presenting the primary function of teaching and learning. Nevertheless, there are numerous different acoustic events carried out in classrooms, which require specific acoustic conditions to support the learning experience. These spaces are not single-use, they are multi-use or flexible, and for this, simulation is vital to understanding how these spaces perform in different situations. A gap in literature exists whereby virtual New Zealand classrooms comprising of physical and oral data attributes have not been holistically detailed. Thus, this paper's aim is to develop a set of virtual classroom environments by manipulating secondary data from existing studies. We will detail the development of 20 virtual New Zealand classroom environments, so 5 classroom types cross-multiplied with 4 oral situations seen in classrooms. To simulate acoustics in an architectural space, there are certain inputs which are required: software instructions and a virtual environment. The virtual environment is comprised of various physical and oral attributes. We started with the physical attributes. So first we assembled and extracted data from the New Zealand Catalogue of Standard School Building Types. Next we performed building attribute analysis using statistical mode analysis and equivalent percent representations. After which we created the physical profiles using covariate adaptive randomization, and we defined and designed the model using Autodesk Revit and 3ds Max. These are our 5 final physical profiles for the classrooms. So along the top we have the number classroom, the dimensions, the ceiling shape, exposed structure and ceiling material, the floor type and covering, wall construction and insulation, the glazing, and the layout of furniture and the occupancy level. We can see an example here of one classroom which has been modeled on Autodesk Revit. And this is that same classroom model which has then been inputted into 3ds Max so we can later combine it with the oral situations. We then moved on to the oral attributes. So we started with our data collection of Brad Bear's study of New Zealand schools, and then we went through oral situation refinement using oral trend analysis. Next, we designed the oral profiles using iSimper acoustic code processor. So here are the 4 final oral situations from A to D. So we talk about what New Zealand teaching approaches are included in each situation and a representation of that as an image, the number of people speaking in this situation, their voice intensity and the decibel level of this, and the approach that we use in iSimper to represent this situation. So here we can see those final physical classrooms that we designed in 3ds Max have been imported into iSimper. So now we can define the oral situation within the classrooms and we can represent that in the physical space. Alongside this, for each surface material within the model in iSimper, we have to define the absorption coefficient spectrum and the diffusion coefficient spectrum. So along the left column, we have all of the different materials used in those physical classroom profiles, and then we have the spectrum between 125 and 8,000 Hertz displayed below that. And with all of this data, we were able to demonstrate our virtual environments on iSimper. This quote says, "Essentially, all models are wrong, but some are useful." Simulations can be used to alleviate some of the challenges with designing and optimizing technology. But of course, acoustic simulations present their own set of challenges. An example of this is that incongruities exist in the field of such simulations around the optimum level of detail for simulated geometric models. The level of detail is quantitatively defined by the number of surfaces in the model divided by the 3D model volume. It is widely believed that model approximations with lower levels of detail achieve more accurate results due to user compensation of assigning less realistic scattering coefficients to reflect actual measurements in space. Let's consider this level of detail theory in our model. So in practice, the oral attributes of the virtual environment would prove to be an accurate software input. However, the 3D geometry input would not be. This is because iSimper performs more efficiently and accurately with simplified geometries combined with precise absorption and diffusion coefficients for each surface. This means that before inputting the model into iSimper, it should be simplified into basic shapes. Interpolation should be used to obtain the coefficient spectrums for each simplified surface to accurately represent the specific and unique distribution of objects and materials on that surface. Nevertheless, the final physical classroom profiles are shown here in a detailed form for broad access and easier transferability into other architectural disciplines and simulation typologies. This paper offers the development, detailing, and demonstration of 20 New Zealand classroom profiles which can be used for software simulation. Benefits from the paper are experienced by those who require typical classroom profiles for simulations in both industry and academic fields, including but not limited to classroom architecture, classroom acoustics, and general acoustic optimization. Despite how this paper presents various physical and oral characteristics of New Zealand classrooms, this does not mean to say that classrooms in other countries would not see value in these demonstrations. Many classroom attributes could be very easily altered or transformed in some way to represent a variation of the classrooms seen here. Additionally, if the classroom profiles are used to simulate and test an architectural technology, by comparing the pre-test and post-test outputs, the statistical results would be accurate as they are presented in a relative context, the post-test data relative to the pre-test data. Thus, these profiles can be used universally to quantify general technological effects in classrooms. Thank you.